So once again, we welcome you all for the next session for this day 3, session 6, the continuation of yesterday's session, as this preceding session, that is IoT. So we would like to invite our renowned alumni, who is also an electrical engineer in NEI Electrical Power Engineering Inc., Michigan, United States, Engineer Pratap sir, to deliver the next session on the topic IoT in power systems. Sir, over to you, sir.
Thank you very much, sir. Let me share my screen.
Yes, sir. It's visible. Yeah.
Okay. All right. Let's get this started. Those who attended yesterday's discussion would know by now that I like to keep things informal, have some fun. So, like I said yesterday, this is not a presentation, but rather more it's a discussion. So feel free to chat, unmute yourself, ask questions. If you don't understand certain terms, feel free to interrupt me and stop me and ask your questions. Uh, Another thing I would say is everything that I'm sharing here is from my experience. I'm not presenting bullet points or data points here. Whatever I have faced in the industry while working is what I'm going to present. So that also uh, leads to say that I am not an expert in this uh, in this topic basically, but I am I'm a user of this technology, IoT technology, um, and I put together lots of devices in order to apply them in power systems. So I need to have the working knowledge, the basic knowledge of these things. So I do have a lot of experience, and I try to break down everything into simpler terms. So that is how I basically learn. So um, so I try to break down everything in simpler terms, so it's easy to understand. And I would also be switching the windows. It's not just presentation slides here. I'll be going to browsers, showing you certain stuffs, and then perhaps maybe sketch some drawings here and there. So with that, let's go to the next slide. So networks. Networks is not something new. Networks has been there for a long, long time. And in fact, when we are talking about power systems, uh, the very first commercial operating power plant in an urban setup, meaning in the city, was the Pearl Street Station by Thomas Edison, and it was in Lower Manhattan, New York City. It's a very dense, crowded place. Uh, but he envisioned that we need to have power plants here, so it's easy to distribute to people. From there, we have come to a whole electrical network we call now a national electric grid, and it's all over the world. And every country has that, and it's even connected between countries, and it's a giant network now. So this network concept is not new, so it's been there. uh, Basically what in the power systems what we do is there is a generator or source, multiple generators, we call them sources, and then it gets distributed, and there are transformers that help uh, bring the voltage up or down based on where you are in the power system. And then you have motors. 80% of the loads are motors, and some of them are other loads like static loads and stuff like that. But basically, this is it. That's the entire network. Right from the beginning, when power generation was the thing, like hydropower plants started, this is what's happening. But what we have been doing from that time is we have been continuously improving the efficiency. So let's take an example. Uh, Back when transformers and generators were first commissioned, they were so huge because they would need clearances between phases, and there'd be heavy steel and stuff like that. But those are becoming compact and smaller now because of other inventions happening in industry. Uh, like for example, plastics. So plastics came in, and we started using them as cable insulators because they have higher dielectric strength. Before that, they would use paper and oil as insulation. But since plastics have more dielectric strength, that's been used now. So all the control cables and even power cables um, have some sort of high dielectric strength insulators. The same way breakers were so huge, in the early 1900s, but now breakers are small. Although they need clearances in high voltage situation, the operating mechanism have come very, down in size. Similarly, CTs. CTs were one of the untouched parts in the power system, CTs and PTs both. Uh, they were huge. They have to be wound, and you cannot open circuit a CT. It's dangerous. But now with advancement in technology, we have optical CTs. We have they called it a rope CT or Rogowski coil CT, which is a low energy CT. So such things are happening, continuously improving, so that the efficiency of the network is increasing. Similarly, on the protective relaying side, that is my area of expertise, if you will. So from electromagnetic relay, sorry, I'm sorry, electromechanical relays. When it initially started, now we have come to we transitioned from there to solid state relays. So it brought the size a little bit down. Uh, During electromechanical times, every single phase had a separate relay. For example, if you have an overcurrent relay, A phase, B phase, and C phase each will have its own relays, and they'll be huge, tall, and heavy. And it's a very delicate equipment, so you have to tune it very precisely in order to make it work correctly. But then, as we had solid states come in, all those sizes started to come down. And then we started having digital relays, and it even got even more compact, and it started to combine protective elements together. Like you would have overcurrent, under voltage, over frequency, under frequency, over voltage, under voltage, everything in a single box. Instead of separate relays taking up an entire control panel, you will have probably one or two relays to do the entire job. And now we are in the era of IEDs. We don't even call them relays because it's not just protective relay. It also does more than that. Like for example, you can get a transformer monitor relay. Um, Let me switch the screen and show you an example. Let's start with the motor protection relay. So this is a motor protection relay, but we call it motor protection relay, but we do have a lot of other stuff going in here. So if you got digital inputs and outputs, which are also fast, and then you have analog inputs, and you have current differential and CTPT inputs coming in. And you also have something called RTD inputs. That is resistance temperature detector. What it does is you can take RTD sensors, which measures winding temperature, and bring that directly into this relay. Think in 1950s, they still had this technology. So nothing changed. They still had this technology, but you would have a separate device just for this purpose, just for temperature measurement purpose. And motor protection was a separate relay. But all of them have combined now along with other features. Similarly, here, if you take this is a transformer monitor. This is not a transformer protection relay, but it's a transformer monitor. Same like the motor protection relay, it has communication capability, analog inputs, digital inputs, and RTD input. So it can take oil temperature, winding temperature, all those can can come in. Now think how this was back in the 60s and 70s. It would be probably like this. You still have this on the transformers, don't get me wrong, but this was the only way to measure a temperature of a transformer. An operator had to go physically go make rounds in the substation yard and take readings, which is still happening. I'm not disqualifying that effort. You still have to walk around the substation yard. You have to physically check stuff. I have been an operator in my past work, so I have done all these things. But at the same time, you would also get information directly from the transformer into the relay, and the relay will be connected to a network and finally to a SCADA. That is possible because of the advancements that we have had, throughout these years. What else have we got? This is the actual transformer protection relay. It has a differential. Okay, I wanted to show this one. So this was the low energy, I think LEA means low energy application, current and voltage sensor output. So you don't have to bring in an actual CT and PT control circuit from the transformer CTs to this relay. You can just have those rope coils, CTs, or even nowadays we are starting to see optical CTs that can be connected. So see what all is available. Just the overview. You can have 2, 3, 4 winding current differential. It's very secure and dependable. There is transformer monitoring, like I said. You also have the legacy 4 to 20 milliamp. And I don't know if you have paid attention in Giridharan sir's session day 1. He said about the 4 to 20 milliamp. That has been there since the 60s and 70s. But that is still there, just in case, if you want to retrofit a new digital relay in an older substation, you can still use this. And then the famous buzzword of the 21st century is the 61850, which is fast communication method. So all these are all, and metering and reporting is there. So sorry, I keep on going. Web server access. So you don't have to have a SCADA dedicated. You can even remotely log in through web access. So all these are bundled into now a single device. So it is called as appropriately intelligent electronic devices. I'm not entirely sure about the intelligent part. We'll talk about that later, but it is definitely a multifunctional electronic device. Oh, I also forgot to show you arc flash sensors. So this is a feeder protection relay. You see this probe coming out. So this is basically an arc flash sensor. When you have a fault, there's a arc flash happening. So this measures the intensity of the light, and there is some logic running in which we can program. So let's say if you have a flash of light and also you have high current over a threshold, then you can AND that logic, right? The digital bit coming from this sensor and the digital bit for overcurrent can be together used in a logic to determine there is an arc flash event, and you can trip immediately. That was not at all possible back in the 60s. And again, this is in addition to all other conventional protections that you would have. Is there anything new? So there's lots of communication protocols, not just one. There's so many communication protocols that can use in one IED. The next one is about periodic maintenance. So how we used to do periodic maintenance back 50s, 60s, when there was no communication networks, is people would go on site, take samples and measure stuffs, get back to the lab and conduct the analysis, and then say, okay, this transformer or this breaker is going bad. We have to do some maintenance on this. Uh, and then we started having hardwired sensors. So you would have sensors in the transformer, but they'll be hardwired all the way back to the control room, and or a control house where you have a relay or a monitoring equipment. And then during 80s and 90s, when communication protocols started to come in, so we developed SCADA, so which you can supervise, uh, control, and acquire data. So that happened, and then we came into the era of continuous monitoring, where the sensor will continuously send that information over a period of time, and you can trend it. Um, then we are now going into the era of predictive maintenance. So you don't have to go and check in a given time, like once in 6 months or once in 3 months, however the maintenance program is. You can actually get the data stream and predict what's going to happen in the future. So we have come from physically going to the equipment, noting down the information, to actually getting a stream of data, and then predicting what's going to happen in the future. Um, so this is one one example. Another example is thermal imaging. Thermal imaging is you take an IR camera, infrared camera, and you see through this camera your equipment. Like it could be a switch gear, it could be bus bars inside a switch gear, or it could be motors. It could even be breakers to check loose connections. So inside in the IR camera, you can see which parts are cooler, which would be mostly violet or blue in color, and which parts are hot, like it would be orange. There'll be orange or yellow glow. So, and by seeing that, you can say, okay, this has a loose contact, so maybe we should tight this when we shut down the plant. Uh, but nowadays, you can fix a camera. Like for example, if you want to measure the transformer temperature, you can fix a camera. Using the camera feed, you can actually live stream that and start collecting that data. And over a period of time, you can see which part starts to get hotter, and that's where you would actually go and do the maintenance. But in the 60s and 70s, you won't have this information. You would just go, okay, transformer maintenance, yes, that has to happen once every year, and that is how the standards were written. But with the advent of these IoT devices, it's becoming easier now to do maintenance. Some other examples are broken rotor detection in motors. So if a rotor, one of the slots, if it's broken, the waveform changes. So you can actually detect that um, and do some maintenance. Then open phase detection in transmission lines. That is another thing that you can detect. There's a new technology that uses traveling waves to detect this open phase, and it happens in microseconds. So one of the biggest problems in America, at least in the western side, is wildfires. You have a large amount of forest that go through this hot season and everything is dry. And you have transmission lines in those areas. So if a conductor breaks and falls down, it's a fault, yes, and some relay will detect it and trip it. But in that gap, in those milliseconds, you will have an arc developing, and it will fire the dry leaves on the ground, and it will immediately catch fire. Believe it or not, there's always some wildfire going on the western side of the North America, not just US, North America, all the way from in Canada, on the Californian side, on the west side. There's always some wildfire going. The point is, it makes to the media when it's not contained, uh, um, or else they don't just report it. because it is well contained. They know that there's fire going on. And I don't remember exactly the year. Maybe it was 2017 or 2018. Um, a major utility company was sued by the state government because their conductor got broken, and it fell on a tree and it started a wildfire. It was not, they were not able to contain it because it was a windy season. It was easily spreading out. So all such things can be now detected, prevented, through these devices. And like I said, we have been having these networks in the past. Like we had some networks, either hardwired, and then when SCADA came, there was serial communications, which is slow, but still it's some form of communication network. But it was truly when internet came on, when that's when people started to realize, oh, okay, we can actually connect more computers across continents and make that happen. And as the demand grew, the cost of the World Wide Web came down. The internet came down. Actually, the internet was invented for the U.S. military during World War. But then, as it became commercialized, it became cheaper because the demand grew up, and now we are talking about networks. So point here is networks is not new, it's been there. But what's interesting is we are now connecting stuff that we didn't even imagine that can be connected and communicated. For example, light bulbs. Who knew a light bulb can send information to your phone saying, I'm on? And then if it's on, you can manually switch it off through your phone, or you can make an automation to say, okay, when it is daytime, you have to switch yourself off. When it's nighttime, you have to switch yourself on up to this time. So you can do all sorts of stuff. And when I talking about breaking things into simpler terms, I don't take the word Internet of Things just as is, because it is basically, it could be called as network of stuffs, right? Network of things or anything. I'm just, for fun in this presentation, I'm calling it network of stuffs. Any stuff. You can take even toothbrush. Some toothbrush are electric now, and they can send you information. It's becoming that insane. Every single device that you can think about can now communicate. So I'm going to call IoT as NOS, right? Just for fun. It's not an official term. Nobody calls this. I'm just trying to keep this light and informal. That's it. Um, what was the state when communications, World Wide Web started? So we had traditional servers. They were bulky, consuming a lot of power. They were fragile, so they had to be kept in a very secure area, well air conditioned place, and it's not available for public because it's not something anybody can go and interact with. And it was slow. It was hard to maintain, right? But now we have come to, like, you can connect, like I was saying, you can connect anything. There's no limit for our imagination. Refrigerators, the refrigerators can now see if a section is empty and can place an order directly for you. If you give the permission or access, it can do it for you, and it can replace, and like it can order, and let's say through Amazon it comes to your home, and you can get those products, and you can refill the refrigerator. Lights and small sensors have become commercially available. Like, for example, temperature, humidity, air quality monitor. These are all can be useful for someone who is sick at home, doesn't can't go out often. They want to be in a under a care. You can buy these cheap sensors. It is probably 50 rupees and 60 rupees. You can buy these sensors and keep to maintain humidity and temperature and also air quality. And from the previous presentation, we saw you have wearable devices as well. And it has gone to an extent where you can do it yourself, DIY. So it has become open source now. All these are available. You can put together your own network. in your home, right? The only thing that is still questionable, like I said from the last slide, is it smart? Because we have this tendency to tag the smart word to everything, right? Like, smart. What do you, let's take something. Refrigerator example that I was giving you, or even the lights. The lights can communicate to your phone now, or it can be communicating through a network, and now we term it a smart light. Um, which is which was the buzzword when smartphones came, but the smartness is something that keeps evolving. I think you would agree, um, because the smartphone that we saw in 2006 now seems a dumb phone to us because it was doing way less stuff than it can do now in 2025. So the smartness is evolving. That's number one. Number two is, it is not always, these devices are not always connected through internet. So let's take a step back and see how the communication flow happens. You have some device, right? It has sensors that collects the data, and then it also has an integrated circuit with some software, could be embedded software on external software that will process the information, and then it will connect to some other device or network, basically exchange data. It could be one way or both ways. It's one way. If it gets back information from another device to control it or do something else, then it's two way. And then that is basically it, the network of stuff. But if you do this over the internet, let's say you're sending, you're looking at your safety camera at your house, but you're in your office. In your mobile phone, you can see if anybody's walking in front of your house or not. So you're actually accessing that camera's live feed through internet. So then, yes, it becomes an internet. It becomes an internet of things. But in the power system world, this is not common. That is why I'm stressing this point. In the previous presentation, it was very, interesting to imagine, RoboCops and other stuffs, wearable devices that monitor your heart rate and everything. It's all very interesting stuff. But when it comes to power systems, not everything is connected through internet. There are a few wide area monitoring, which is very, very, very limited and has to be secure. So IoT to me is a misnomer, but that's what we have been now stuck with. Okay, now let's go into power system. From a generalized view, let's go into power systems. I'll be giving a little bit more, examples here. So what does it do in power system? It's exactly the same thing. There's nothing magical here, and there's nothing special that you have to learn. Basically, it's the same bunch of sensors now can communicate to other devices, which, like I told, we have been doing this for over 20, 30, 50 years now, but it was slow, or it was big. Now it has become compact. It has become faster now. I'll give you one example, how the data collected in through these IoT devices it could improve resilience in power systems. So for that, I wanted to explain you what DC systems in power, in substation is. So let me probably take this time to draw out. Let's see if I have my whiteboard from yesterday. There you go. So in a typical substation, right, you have power coming in from the utility, and then you have a transformer which steps down. Let's say this is an industrial substation, so it's receiving power. We don't care about the details now. What transformer? What's the voltage? And where probably you will have a main breaker, and then you have a bunch of loads. Then let's say you have motors here, and it goes to another panel, maybe low voltage breakers, maybe. So the power would now normally flow from here all the way to the loads, but the controls are done by relays, right? So you have a CT and maybe a PT here. And you'll go to a relay. So this is, it's getting the CT information, current information from here, and voltage information through this PT. But this relay itself needs power to operate, right? It cannot power from this way. It could power from the PT. That's one idea. Instead of just getting the voltage information, it could actually power itself, because this is going to be, let's say, this it's this 11 kV bus, but this PT will take it down from 11 kV to what's the secondary of PT in India? Can anybody tell me? It's a standard. Can anybody tell me what's the secondary of a CT? What's secondary voltage? I'm sorry, of a PT, potential transformer.
110 volts.
Very nice, 110. In the US, it's 120, but it depends from some systems, or also depends on the relays. It could vary. It could be 110, it could be 115. So anything. Anyway, 110. If this relay is able to, by the way, it's 110 volt AC, right? That is where this is what I'm coming at. An AC supply, and if this relay is able to work on a 110 volt AC supply, good. We can buy that. But the problem here is, let's say you lose this utility. Okay. Now the power to this bus bar is lost. Power to the relay is lost. The relay is basically dead now, right? You cannot do anything. And now let's say the power comes back. The relay takes probably 5 to 10 seconds, or maybe even more, to boot up and load its program, refresh everything, all the status of the digital inputs, analog inputs, everything. And by the time a fault occurs there, it is not going to see the fault current. So it is not going to issue a trip signal to this breaker. And that is why it is very common to see DC systems in substations. All these IEDs are actually powered by a separate battery, right? Plus minus, you send that. Common that I have seen in US is 24 volt DC, 48 volt DC, and 80% of my projects are always 125 volt DC. I've also seen 250 volt DC, but this is where it's common. So how this works is you take the power from the mains, and after stepping it down, you take it to a battery charger, and the battery charger converts AC to DC, and then it charges the battery. And when the power is lost, there is no power here, the battery starts to drain, keeping the relay operational even though the power is lost. And then when the power comes back, this again starts charging the battery. Now, okay, so this guy is a battery charger that I have frequently specified in my projects. It has good, nice display showing what's the battery voltage, what is the incoming AC voltage, has breakers and everything. Again, to emphasis, this has been there since 70s or even 80s. People would go and there would be an analog voltmeter and ammeter here. You can actually record those values, in person. But now these guys have communication capability. So it has serial communication. It has Ethernet-based communication. It also has IEC 61850 communications. So now this battery charger can report a lot of information. What is the battery status? What is the voltage of each individual cell? Because it's usually 2 volts every cell. So to make 125 volt, you at least need 60 to 65 cells. We keep it 65, so the total is 130 volt, just in case. If it drops to 125 volts, and we can keep it operational. So it can tell you that. And in substation control houses, you will have a hydrogen detector in above these battery cells, because these cells will leak hydrogen sometimes. So it can report all those information back to the SCADA or any relay or anywhere. It can, as long as it has Ethernet connection, it can be on a network. Or if it's in a serial communication, it will be on a separate serial communication network. So this data that we have, it empowers us to get insights from from the system, basically. So it improves resilience, and then it also enables resource management. Like I was saying in a few slides before, how you have advanced IEDs where it can measure real-time data and everything. One such example is the power quality. I think I showed that, right? Or maybe not. So this power quality meter, what this does is actually it gives you the power quality information at a high speed, and before this, how it was done was you would have a Fluke meter or some other company's meter that does this power quality analysis. You would go to the site, you would install it, and you would leave it probably for 7 days or however long you want to measure the load profile. And it will collect data like harmonics and is there a voltage flicker or not, sag, swell, everything. Then you take that device, come back to your office, upload it in your computer, and then do your analysis. Okay, I see a lot of fifth harmonic, so maybe this industry has some problem. So that is how you used to do. But how long will it take, right? But now you have these IEDs that can actually send all this information directly to your. You even have web access for this, so you don't even have to be in a control station in front of your SCADA. You can just remote from your, you can log in from your phone or any computer which has internet access, and you can actually see what's going on. So now what happens the same way. This is even becoming even more advanced. It's actually not yet available in the market, but they're now going to do time domain power monitor instead of using the regular CTs and PTs to measure everything. They're going to do that in a time domain, and it is insanely high sampling rate. It's like 14.4 kilo samples per second. Let's do a math. I think I should. Yeah, I was getting ready for this, and I actually did. 14,400 samples per second, right? And in India, we have 50 hertz. So in a second, you will have 50 cycles. So per cycle, just one cycle, one sinusoidal wave, you'll get 288 points, sample points. And if anybody knows the basics of digital signal processing, you would know how high that number is. Versus the old relays, which used to do slow communication, we got 4 digital points per cycle, just 4. So by getting all these high sample rate, you can actually allocate resources. You can actually send. You can make you can say, okay, this feeder is getting high harmonic level. Or in case of transmission line planning, I can give one example. You would monitor the current flow in a transmission line, and you could also take in the weather data. Now, weather data would come from a sensor, and load flow would come from the current flow would come from CTs and PTs. Then you make a comparison saying, okay, maybe only during summers this transmission line is getting overloaded. So maybe we should allocate more generation resources during summer. Or if there is no other resources, you should actually put a parallel transmission line. So it helps in long-term planning. You can you manage the resources based on the information that you get. The last is optimization. So instead of doing repeated stuff again and again, where you don't know, for example, in case of maintenance, you do certain maintenance in a regular period, but you don't know what's going on in your system. You just do blindly. Every 5 years, I have to test my breakers. But do you have any other information what went wrong in those 5 years? We don't have. But with these IoT devices, with these sensors communicating now, we can have that information, and you can optimize. You can make informed decision, both at operator level. They can take information decisions based on this, and also all the way up to the stakeholders. The business people who are owning these big facilities that are multi-million-dollar facilities. They can take informed decisions earlier. So it optimizes that. Then I think I already covered this point. Like the network of stuffs has already been there since 1950s. Like you had the SCADA, but they were bulkier. They were dedicated computers for that, and the relays can take their own decisions now. A common example in power systems is the smart meter. Again, I have a question mark on the smart because the only thing that changed between the old meters and the new meters, it became digital, and then it got the communication capability. So to me, there's nothing smart there. It's definitely advanced. I'm definitely for that, but smart, no, not yet. But that smart meter, or it is also termed as advanced metering infrastructure, AMI. That is the key component in a smart grid. When you say smart grid, again, let's not go into that smart part, but when you say smart grid, it starts with the digitalizing of the meters. And once it starts having communication capabilities, you can take it to next level. I think I can give you one personal experience that I have with this smart meter. In the place where I live in Michigan, the utility has a program where you can enroll by supporting the utility, meaning during summertime when the grid is stressed, they will ask you to reduce your load, or in turn they can actually control the loads in your house. So for example, my smart meter can talk to the utility, meaning it can communicate to the utility, and also there are some other devices that it can communicate to the utility. For example, the AC controller. Okay, so during hot summer times, what usually people do, everybody puts AC in the coolest mode. Everybody wants as cool as possible, and the grid is getting stressed. Now, if you enroll in this program, they will, I think it's just 4 days a year. That's the limit, because they cannot do every single day. That will not be beneficial for the customer. So they choose 4, the most, they call it a red day. It's most, very hot and very high load condition. The utility can remotely access your thermostat here and control your AC settings. And they can bring it down like 4 degrees or 5 degrees down. You'll have your AC. They won't shut it off, but it will be brought down. And if they do this for, let's say, 1,000 homes, that makes a big difference. But what I'm trying to say here is, see how how these IoT devices are helping the grid. And you might ask, so what's the advantage for the customer? If you enroll in that program, you will get a lower electricity rate. Like compared to other people who have not enrolled, you will have a less rate throughout the year, not just for those 4 days. So there's like give and take for these situations. This one example from personally that I have seen. By the way, I have not enrolled in that program. What is next? Okay. So now in 2025, just like the previous presenter told, we have so many interconnected devices, so many IoT devices that talk to each other. One project that I have done is in a manufacturing plant. They manufacture gas tanks or petrol tanks for cars. Pressures and sensors around certain machines, and that is compared with your metering devices, how much energy it's consuming. And also some of the safety devices have been tied into the same network. So all these data are brought together, and there is a data analytics team that looks at this and takes decisions based on that. And they also create automations based on that. So this is actually called IoT, Industrial Internet of Things. So that itself is a separate domain, and then there are experts working on this. So that's another interesting thing that I've seen. I can also show one more. This is basically this is equivalent to the IEC 61850 protocol or standard. And but this is a proprietary technology called TIDL, TIDL, time domain link technology. So what basically it does is, again, going back to that drawing, you have CT and PT in a normal substation, and you'll have 3-phase coming from this ABC and neutral, and 3-phase coming from this ABC and neutral. So that is how many control cables? You have 8 control cables coming from just one CT and PT. You would also want CTs to be measured for these relays, these feeders. So the CT is there for overcurrent protection. So every single feeder will have its own relay. So that's 4 control cables per feeder. And on top of that, if you have differential protection, you'll have that as a separate connection. And that's 3 and 3 is 6 relays. And then if you have bus differential, that's even more. I don't have a space here, but anyway, the bus differential will go across all these feeders, and from top, that's relay. So when you start adding like this, and this is a very simple substation. If you take a giant substation, you will add up a lot of control cables, and that is a lot of copper control cables, and copper is costly. Now with this technology, which is equivalent to the 61850, everything is converted to fiber. So what basically happens is, if you see this merging unit, you will have CTs. I don't know if I can draw here, maybe yes. So let's say you have a line, transformer, bus bar. I'm sorry, that's supposed to be a square, but it's not drawing a square. Breakers, and you'll have CTs. Let's take just the differential of a differential protection of a transformer, and you'll have this connected. And this TMU, tidal merging unit, will stay as close as possible to the transformer. So if you have a transformer, it will be just underneath the transformer in the control panel. So from that place all the way to the control house, you only have fiber. And think how many copper control cables got replaced by fiber. So this is also one of the advents of IoT. That merging unit can be called as an IoT in the power system application. And the last one I want to say here is about AI in power systems. Level of using data and communication. When I was at KLN, we were working on optimizing algorithms, and we were calling that AI, artificial intelligence, very smart in 2007. But now, like I said 2 slides before, you can actually program in such a way that it can learn and predict fault in few years. That is already under research now. I've seen so many research paper using machine learning and all those, to learn the fault waves, and thereby predict in the future what fault is happening, and like, is it single line to ground fault, double line to ground fault? If it has happened, what are all the sequence components? Everything it can do. So that's a future. It's coming up now. Okay, some of the applications. This is just few, but I want to give you an idea of what all is in the power system as applications. So first, we all know smart grids. Everybody knows smart grids. I don't even have to explain. But to define that in the context of IoT, we can say that anything that interacts with the grid, the power system grid, beyond the major equipment. Like, I'm not talking generator, transformers, all the loads. Those equipments can be called as IoTs in smart grids. Like I said before, the advanced metering infrastructure or smart meters, and thermostats that I told that can be used. Lots of sensors are now directly getting integrated into the power systems. So all these items are coming in, and I can keep naming them. So that's IoT's application in smart grid. Then predictive maintenance, like I told before, we can get a trend data, and we can predict what's going to happen in the future, because proper maintenance and in order to extend its life. I will say this in context of predictive maintenance. I have worked in flood water pumping stations. So this is just a substation that has huge motors. I'm talking motor will, if you're in the ground floor, the motor height will be up to the first floor, like touching at least up to the second floor. It's that high, and it's like 7,500 HP horsepower motors. They all stand vertically down, and you're on the same floor. You have the switch gears. The substation is there. These are dedicated pumps if the city floods. So if there's a lot of rain, and then if there's flooding happening, these pumps would turn on, and then it will discharge the water into the nearby river or sea, whatever is closest outlet. Now, floods don't happen every single day, right? It happens probably once in 3 years, but these pumps or motors should be ready to turn on at that instant. So a pump will not be running for maybe 1 year, and then suddenly a flood occurs. You need that pump to start. It's a giant rotor. You need to turn that, right? So what people do is they do trial runs, and they also have spare pumps. Like, if one fails, you have a backup. So redundancy is included. But when you do trial runs with just a little bit of water, you will get these data streams from the IEDs that I just showed you. You can trend those, and you can see, okay, something is wrong with this motor, so let's not schedule this motor or pump for an actual event. so they will schedule something else. So you can do all those predictive maintenance beforehand. And all this is possible because you have these little sensors now that are able to communicate easily over fiber or Ethernet or whatever the communication medium may be. Energy management systems. Okay, this is another example from a project I worked. So there's this building. Basically, that building hosts conferences. It's a huge building, and in a single day you will have at least 12 conferences going on. It will be a career fair, or it could be something about a product a demonstration. I've even seen boat shows. Like, they bring boats and they demonstrate, this is our new boat. This our car trade shows happen. So this is a huge facility, and the revenue is at least $1 million per day. So it is such a huge place, and that place gets 3 different utility incoming sources, because it is that important to have electricity there. If one source fails, it transfers immediately, automatically to the next source. So such a huge place, and it has 33 feeders per bus. So 3 buses, so 99 feeders. So think about that. 3 incoming utilities, 3 giant transformers stepping it down, and then 3 main breakers each going to a single bus, and they're tied by 2 tie breakers, and every single bus has 33 feeders. There are so many loads there. So what for such customers, what the utility does, they are not just paid for the energy consumption, the kilowatt hour, or the kilo power hour, not just the reactive power. So it's not, you might have heard about, industrial customers are charged for maintaining power factor, that is reactive power, and also the active energy consumption. Whereas residential customers are only paying for active energy, kilowatt hour. On top of that, industrial clients like these high demand industries, they are charged on basis of demand, like how much demand they are placing on the grid. So for example, their load is I don't remember on top of my head. Let's say it's 2000 kilowatt, just the demand. Okay, on a given day, the maximum demand that is put on the grid by this industry or this facility is 2 megawatt. Now, that utility has to maintain the infrastructure to provide the 2 megawatt, because utility must be reliable. So they have to maintain the overhead conductor, they have to maintain clearances, and they have to have resources to power up this facility, right? So every such huge demand, customers are charged by their demand. Now, how you do demand calculation is you add all the loads together, and then you put something called as diversity factor or demand factor, because let's say you have a light. The light bulb does not glow 24 hours a day. The light bulb, it is, and say, this is the demand of my facility, and you would give it to the utility, and they would charge you based on that. Now, demand can increase because you might add another section, or you could expand your building. So every 5 years, what the utility does is we have to submit a revised calculation. Okay, so all this has been happening for so many years. This is how static demand calculation happens. What this facility did was they started incorporating these high sampling IEDs in their meters, and they started to record their demand on a continuous basis, not just like a theoretical calculation, but they were measuring on a continuous basis. So after 8 months, they projected that their demand was way less than what was theoretically calculated. So at the end, they submitted back another application to the utility and said that, see, based on these values, we have a lesser demand, so we want to reduce the electricity bill. And you won't believe, they reduced $2 million per month just for, per year, just by trending these demand values, and that's happening because of these devices that could communicate over network, and you can trend them and store the data. So that's one example of energy management. They actually were able to tune their the building AC and heating machines, which is called as HVACs, and using that they could reduce the demand further, and they were getting benefit out of that. Another thing is renewable energy integration. This is a separate topic because you could you could say that this is just as equivalent to adding any other energy source, not just renewable. But this is because IoT has been driving the renewable energy integration very fast. Like I'll give you one example. Back to the drawing board. My computer is really slow today. Okay, we'll use this. So in a typical renewable energy power plant, you have a transmission line, and then it's connected. This is called POI, point of interconnection. Then you'll have your substation fence here, and then you'll have a transformer, high voltage breaker, low voltage breaker. Then you will have all these feeders, but these are not consuming power. These are actually producing power, I mean sending power to the grid. And then you will have, this is usually 34.5 kV. Then you will have fuse. You'll continue down. This is another transformer. Then you'll go to the inverters. Then you will have solar panels here. So you'll have a lot of such strings and strings of inverters. The same way you could have battery storage or whatever. Now, okay, let's do battery storage as well, because that's another example, interesting example. So you'll have the same inverter, then you'll have battery storage. I don't know how to draw battery storage. Let's just assume this is batteries. Same way, you'll have a lot of battery storage units. Now, one of the problems with renewable, like complaint in the renewable industry, is that it is not giving reactive power support. Because with rotational, generators, it has inertia, and so it can support for any transient disturbances in the transmission line. But since these power electronic devices or the renewable sources are not rotational, for example, PV and battery, they don't add this inertia to the system. And what nowadays is happening is that so when I draw this, I'm drawing almost like this 80 to 100 PVs. Each of them will be like 4.4 MVA. So think about that huge plant. Now all these inverters can now talk to each other. So they all talk to each other. Instead of acting as a single 4.4 MVA power source, they all can combine. So let's put a fiber between them. They all can combine as one giant source, and now they can start adding stability to the system if needed. If there is a huge disturbance in nearby place in the transmission line, this can actually act as a steady source, contributing fault currents. That's number one. On the battery side, so you have PV pushing out power into the grid, or if not, you can actually store your free energy or excess energy into the batteries, right? And during nighttime, when PV is not working, your battery can you can discharge and act as a source, and you can earn money using that. So people are basically doing that. But there's also one more advantage of having battery systems. That is called a VAR support. Actually, I think I switched between power system oscillations and reactive power support. So this is power frequencies or oscillation support. This is the reactive power support. What it can do is it can actually take power from the grid, and it can convert. You can actually use that and convert into reactive power and send it back as reactive power. So it takes power from the grid and sends back as active power. So there's no actual uh, energy conversion happening here. It is just taking power from the grid and sending back as VAR, except there will be some losses in the transformer impedances and cable impedances here, but that's fine. But now batteries can act as a VAR source at nighttime whenever it is needed. That is because all these inverters talk to each other. They form one giant source, and they can put that. The other option before this would be to switch in a capacitor bank. So during daytime, when the grid is overloaded and there's reactive power support that is needed, you need capacitor banks to be switched on. And now capacitor banks are usually huge. And then you need to maybe stage them if you want to break them. Let's say you have a 24 MVAR cap bank. If you add 24 MVAR cap bank, that's one stage. And if you don't want that, you need to break them into I've seen 2, maybe 3 stages, like 8 MVAR, but the controls become very complex in that case. Plus, it's a giant 8 MVAR addition. But here, if you have the inverters can tune themselves, and they can actually provide as much as required for that particular time of the day. You don't have to switch on one bulk load. Instead of that, the inverters can find control and add that. So that is one example for renewable energy, how IoTs are fast forwarding renewable energy integration. The last one is demand response. Now for this, I'll show you. I'm not going to draw, I promise, and I'll show you an actual PDF. Okay, so quick introduction to the system. This is a utility coming in. They had a spare utility like for future. So they had 2 incomers, only one was connected, and it goes to a data center. What they did, they wanted to add a backup generator to the system. So we thought, okay, there's a spare breaker here. Instead of using that for a future utility, which is basically the same line, so it is not a backup, because if that line goes down, both the lines will go down. So there's no use of having 2 in this place. So we thought we'll add a generator here. Now let's go into controls a little bit. I don't know how many of you are familiar enough to read DC control schematics, but I can tell you in a nutshell. Basically, think this as a logic diagram. Okay, this is a closed circuit of a breaker. Like this is, if everything gets closed, power from this positive DC power from this would flow through this circuit, flow through this coil, and it will complete the circuit, thereby closing the breaker. Similar way, you would have a separate DC circuit. If any of these contacts close, which means the circuit will get energized the circuit will get complete, and this trip coil would get energized and will trip the breaker. Okay, so what I don't know if you remember from my previous session, I was talking about if you have generators in your facility, you can enroll in a program where when the grid is stressed out, the generator can act as the source. Thereby the utility can take in lots of such small generators and add to the grid, so the stress comes down. Now, it's not a simple thing. You cannot just like that add a generator or connect a generator to the uh, and those contacts are connected for a closed circuit. It's connected in series. For a trip circuit, it's connected in parallel. Now, in order for this breaker to close to the utility should allow for this contact to close. Okay, so there are automatic ways you can make that close, but the IoT point comes in here. I'll show you. So that relay interface would probably look like this. This is a particular company showing, and you see how out 101 says trip, and then out 105 says close. So if you go into trip logic, you can actually define what all stuffs goes inside this to make the trip happen, or what all stuff that goes inside close to make the close happen. Going back here, now this, let's say if this switch is closed, it's a small test switch, and your relay, the customer's relay is wanting to close, but if this is open, your breaker will not close. So in order for the breaker to close, this relay should also, this contact should also close, this contact should also close. Now, what usually they would do is, so what was that contact? Sorry, I'm jumping. It's all or 06. It should be probably 106. I'm not sure. In this case, it's called a virtual bit or a remote bit, whatever may be the case, depending on the protocol you use. You would put an remote bit or a virtual bit in that equation, in that contact out 106. So whenever the utility wants that generator to connect, they will send a close command from their control station somewhere few kilometers down. We don't know where that control station would be, but they will send that information and they would close this contact. So once that contact is closed, they are basically giving us permission to close, and they will call us and say, "Hey, we have a overload condition. Can you please start your generator?" And the customer would start the generator. If it's already running, they'll just issue a synchronizing command, and it will close the breaker. So thereby, this term is called demand response. So based on the grid's demand, the client is responding to that. The generators are responding to that. So that's one application where communications between these devices is helping a lot. Okay, so benefits. I'm not going to throw data points here. We'll just, from what we have discussed so far, we can see what all benefits we get. We get enhanced efficiency, very good efficient way, because devices are talking to each other. Maybe SCADA or whatever other methods, it needs to communicate. It communicates that way. So there is an enhanced efficiency there. You could also actually do real-time trading, meaning, just like stock market, for utility sector, there is trading happening every single day based on how much, what's the cost of energy of a power plant. So let's say an owner owns 10 power plants at different places. Um, if you again think about the flow of data, TTs and PTs would give you the current and potential information, voltage information. It goes into a meter. The meter calculates the kilowatt hour and kilobar hour reactive power. And then that information is taken into a centralized SCADA or any other automation system where it calculates the cost of that day. And then the same thing happening in every single power plant. And whoever is doing the trading, that there's a whole department that does trading. That department can make decisions how much to sell the power for. And at the same end, on the other side, when people are buying power from the utility, they can actually trade and say how much they can buy the power for. And all this happens because of the again, I tend to say smart device, but in my mind it's saying it's not smart, but that's the word we are stuck with. Then obviously improved reliability. If you can do predictive maintenance using these data, then you are increasing the reliability of that equipment, of that you're being more reliable on that equipment. So predictive maintenance, is one way. And then real-time monitoring. I don't know how many of you remember. I don't want to go into the details, but I was talking about a fault location, isolation, and service restoration. FLISR yesterday in overhead distribution reclosers. So by having that real time, maybe I can quickly show. I still have that page. So like, I don't know how many of you remember from STAs. So you can actually draw out, you can make all these UI, and you can get real-time information, the status of each recloser, how much power is flowing through each recloser, and then you can have the data. You can operate it remotely. So by getting that, you're actually improving the reliability of the system. You are reducing power outage duration. So if something trips, you know exactly where to go instead of they say walking the line, meaning, so let's say it trips, let's say here, down here, the person has, the utility crew has to drive all the way to find where it tripped. So instead of that, you're using this, what do you call it, the UI, you can actually see where exactly the recloser open, and you can go there and do your maintenance work or repair work, and that reduces the power outage duration. Cost savings. I already told about the IEC 62850 and SCL tidal technologies, where it is replacing huge amounts of copper cables and into fiber. Now, along with the material cost, there is also labor cost. People have to wire each and every single terminal. So that takes a lot of time and a lot of labor cost. So that all comes down with just few fibers. So maybe just 10% of the work is what is needed. And just a fun fact, because we were talking about layers, the OSI model, in IEC 61850, there are two protocols called Goose and sample values. These are high-speed protocols. When I say high-speed, it is not 1 second or 2 seconds that happens in SCADA world. In the SCADA world, there is Modbus, DNP, and all those protocols transmitted with a delay of 1 second or maybe 500 milliseconds, half a second. That is very long or very slow in protection world. So from the domain that I work on, where you have to send trip signals and close signals, all those has to happen in within instantly. So that is the reason we have had hardwired control cables from the relay to the breaker or wherever. But with goose and sample values, they can send signals in nanoseconds, or I think microseconds. I don't know exactly the timing. I can't recall, but it's so fast. But so how this happens, how they achieve this through fiber, basically through Ethernet, is by just using three layers: layer one, layer two, and layer seven. Layer one and layer two, I don't remember the specifics because I'm not a expert in that. Uh, but it avoids all other layers in between, and then you have the layer seven, which is the UI layer, but where you interact uh, with the device basically. So um, now with instead of using copper cables, you can use fibers to send these trip signals and fast protection messages. So if you want to trip a substation which is remotely located, you can do that now. That's one thing that it's a fun fact. Two layer. I don't know if you call two layer or three layer. And then workplace safety. So in underground vaults, where you have, like in the city, you don't usually typically see overhead conductors. It was usually more underground. So the distribution is underground cables, and you have vaults that you go down in to do maintenance activities. But these underground vaults can actually produce hazardous and dangerous gas, which if you breathe, you will actually die inside that. That's number one. And number two, if there is anything else happening in the system outside, you won't know what's going on. So if someone has to contact you saying, stop work immediately, come outside, someone has to radio or someone has to phone call you, there is no, there needs to be some manual intervention there. But with these IoT devices, there are hydrogen detectors and other gas detectors inside these vaults, and that can directly relay that information to the protection system, and the protection system can trip off the breaker upstream, thereby saving the person. If there's a fault happening somewhere, you don't want that cable to blow up and or that person to experience an arc flash incident. So that hydrogen gas detector sensor can actually send a bit or digital bit to the protection relay saying high hydrogen detected, and then the relay can trip the the circuit. So that's improving workplace safety. That's a new information. We didn't discuss this before. And then environmental sustainability. So obviously, we talked about power support and grid forming inverters. And so as more and more renewable resources come in, you don't have to rely more on the coal and natural gas power plants. You still need them at this point. We're not completely replacing, but with how fast IoTs are developing and how it is affecting power systems, you're actually outpacing the number of the coal plants and natural gas plants. Plus, it is also very fast to install. I have in this 1.5 years with this new company, I've already commissioned almost 17 substations. Every single one of them are 225 MVA and above. So that's a huge amount of generation source that is added to the grid. So renewable integration helps in environmental sustainability as well. Like any technology that has come through, IoT technology also has challenges, and the WIP means work in progress. So definitely these challenges will come down because people are actively researching. There are new products coming out, better efficiency and everything. But as of now, these are the things that came to my mind. Security and privacy is at the top, because now you're sending information through a wide web, a wide area network. Anybody can come in and actually look at your device. So the example that in the previous session that they were giving for insurance company, they said, if you install this device, we'll track how fast you're driving your car, and if you're driving it within speed limit, and if you don't have accidents, we'll bring down your insurance. That is actually true. I have had my insurance call me and say, there is this program, do you want to enroll? But the first thing that came to my mind is, okay, if you know where I am driving, where I'm going, the insurance company may not necessarily use that device, but if that gets hacked, that information is out in the public. Anybody can use it. So that's the first concern that came to my mind. Interoperability. Interoperability means a device directly talking to another device, peer-to-peer communication. This is actually coming with 61850. That's the entire goal of 61850, where a device can talk to another device, regardless of what manufacturer they are. So 61850 standard defines this, but it's still, I would say, it's not full-fledged into the IoT world. It's happening in the relaying, but to bring in other sensors like load tap changers and all other devices that's in the power system, that is not happening at this moment. But definitely, like I said, this is work in progress. So it's improving as we speak. Every day we're getting new features. Data management. There's huge amounts of data now, right? Because we are connecting everything and every single sensor is sending that information. You have huge amounts of data. To manage that, you need a separate data management software or a device for that, just to store all that. And so that's another thing, because you could store all the data in one or two devices, but if it fails, you need to know you need to design the system to transfer all the data immediately to a backup. And there are some ways to do that, but I have not seen that full-fledgedly used. Another thing I remember is about going back to security and privacy is password rotation. So in a substation, you will at least have 70 to 80 IEDs, and each IED will have its own access, like the password, level 1, level 2, and depending on who's accessing it, they will have different levels of features that's enabled for them. But you cannot keep one password, because hackers can come in, they can figure that out, and they can crack. So there is a separate password management software. What it does is it takes all the password and it rotates it. It gives new passwords, and you can actually set that. It's not doing it automatically. Basically, engineers are programming it, but you can set in such a way that it gets rotated either periodically or randomly, whatever it is. So even if an employee knows a password today, it might change randomly next day, and that employee might not get the access. They have to go through that password management software, and they should have access to that in order to get the password of that relay. This helps in the previous example I gave yesterday, where an employee was fired and he hacked the system because he had access. So this can help in a way. Then power consumption. So power consumption right now, I know people have told in this previous session that IoT uses very low power. That is true for small sensors, like in power systems, it still needs a lot of backup power, because if something fails, you need power for a long time. So you have these big batteries compared to the small batteries that you have in the regular IoT devices. Sometimes I have seen they have PV small solar cell on top of the sensor, so that it gets power from that and charges the battery. So that's another thing. We need to optimize power consumption and how to increase the energy density of these batteries. Thereby you can reduce the footprint of the batteries, and you can get more power out of it. Another big problem, speaking of environmental stuff, is how do you recycle these batteries? Is that even possible? How do you collect all these batteries and then streamline it, establish a supply chain, and then replace the batteries or recycle the batteries? So that's a huge problem that I don't think so it's been addressed so far. Reliability, connectivity. Reliable connectivity. This is a huge thing in power systems world. If you lose communications, for example, if you lose communication to take a IoT device, maybe your smartwatch. If you lose communication, it's okay. I mean, nobody's going to die. But if you lose communications in a substation, if somebody's working there, that person can die. Or you can trip off a breaker to a huge section, and people will not have power. Hospitals might not have power. So connectivity is a big thing in power systems world. So loss of connectivity is a big deal. So we do have redundant connections coming in. from two different physical locations. So if one fails, the other one does not. And for like the 3G, 4G, and 5G connections, you will have two different vendors. For example, in India, Airtel and Vodafone. Something that came to my mind. So I'm just saying you'll have two different. So if Airtel goes down, then you'll have Vodafone, or you might have Reliance or whatever. So there are some workarounds like that. But still, if there is a cyber attack and all the communications are lost, that's a big red flag. So connectivity is a big thing. And then resource management. This, if you remember from the previous slide, this is a conflicting thing, because just few slides ago I told resource management is a good thing, with IoT, but here I'm saying resource management is a challenge. Let me show you quickly. So if you see the second point there, enabling resource management, I said these are the stuff that are in power systems, but it's also a challenge, because I quickly want to go and show what's happening. You need to allocate the people who know what they're looking at. Just giving them the data does not mean anything. So I said you get lots of data from these IEDs, and they're in front of the screen. And if the operator does not know what to look for in that, how will he or she take a decision, right? So for example, this is an event analysis. So basically, these are currents, and these are voltages. These are digital bits. So if you see trip went from 0 to 1, so trip happened, and your current went down, which means the breaker opened, right? So I'm able to interrupt what's going on here, but you need to know more. And I don't expect the audience to understand this completely, because this is something that I work on every day, but not necessarily everybody would be working on this. If you see here, it says filtered. Okay, there is also another format you can get this called ComTrade. It's a standard where you know how you put your sample data points into these graphs. With filter, I only have access to certain things. For example, let me check an RMS current. It doesn't show anything. I am getting instantaneous current. I can see here A, B, and C phase, but I'm not getting RMS, because RMS, because this is a filtered value. This is a basic 60 hertz frequency filtered value. There are no harmonics or any other frequencies in this. So it won't give you a true RMS. So that's why it is disabled in this. So I need to know which kind of the event I have to download from the relay and which one to look at. So although I have so much data here, if I don't know what to look for, then it's going to be a challenge. That's what I mean by resource management. You need to allocate or train people to know what this is. And you cannot train everybody, because some people don't have to look at this. For example, a civil engineer or even a business owner doesn't have to look at this. They don't have to get trained in this. But a protection engineer, electrical protection engineer, might have to be trained in this. So that's a challenge. So training and other resource management. And then cost. Cost in general, right now, since this is the new trend or new devices coming up, they tend to be higher. This is true with any technology, right? When smartphones came, they was very costly, and as time went by, their prices dropped. Same would happen, but again, this is a work in progress. And if anybody knows a little bit of evolution, Charles Darwin said it happens through natural selection, because as the demand goes up, naturally the cost would come down. Then regulatory and compliance issues. So in the power systems world, everything moves slow, because it is heavily controlled by regulations, by the government, because you cannot easily trip off any breaker. You cannot cause unsafe incidents. So there's a lot of things that you have to comply with. But that means not everything will be approved immediately. So if I say I want to connect my substation and trip the other substation for such, let's say there's a line fault, they might approve for existing technology. They might not approve for IoT devices, because that utility might not have approved that particular thing. And this is the last one, skill gap. So this is my time to say, please like, comment, and subscribe, because I told the exact same thing yesterday, and I'm telling this today, that there is a lot of exciting opportunities with these IoT coming into power systems. So, but there are not enough people to actually start working on this. And I'm sure there's a lot of research going on in the academic side. Also, there is a research and development going on in the professional side, but people who have to work on this are needed. And if you see, both the pictures that is behind was generated by AI. So I did not make those. So AI is next another thing that we power system engineers need to learn about. And this is a real image. This is not AI. This is an actual person with the networking devices. So thank you for patiently listening. If you have any points or anything that you want to discuss, let's chat. And I'm always available to chat about these things anytime. And you can contact me through these through my email or LinkedIn. We can chat there. So thank you very much.
So thank you so much, sir, for your a brief lecture on the different view of aspects of IoT. Annabelle, ma'am.
Yes, thank you so much, Pratap, for your excellent and elaborate presentation about practical scenario and in power system. And thank you so much. We definitely encourage our students and other academicians to do research in this area so that IoT and cybersecurity can be implemented in this power system. Thank you so much. Thank you for your wonderful presentation.
Thank you, Pratap.
Thank you, ma'am. Thank you, sir. It is actually really happy to see these kinds of forums and discussions brought together, because only when people start discussing about that, there'll be more research and there'll be more interest. So I hope the other sessions go well, and thank you for having me here.
Yes, sir.
Thank you so much.
Thank you so much, sir. Thank you so much. And thank you to all the participants. So there comes the end of day 3, session 6. So tomorrow, as usual, we'll join for the 4th day, session 7, sharply by 6 p.m. Have a good night, and see you all tomorrow. Catch you tomorrow. Bye.
Shankaran,
Ma'am, yes, ma'am.
please stop recording and then
Yes,
we'll
sure.
Okay. Thank you, Pa. Thank you so much.
Thank you.